Howdy, welcome to Computer Graphics, Animation, and Simulation, and today we're going to continue talking about springs, in particular, springy meshes. In particular, we're going to talk about struts, meshes, torsional springs, lattice deformers, and cloth. So, first thing about struts is we need to understand what a spring mass damper system is, and from this little diagram we can see that we have a spring with the coefficient K, the damper, the coefficient D, and the mass at the end. But since this is kind of attached to a wall or something, we would like to actually be able to connect two particles together with a spring mass damper system. So in order to do this, we do it with a strut. And so if you could imagine two masses on one side, and we'll call mass I and mass J, and inside the middle we have the cylinder, which represents both the spring and the damper. And we have a few parameters that we're going to take a look at. So we have the spring constant that relates mass I to mass J for this particular strut, and we have the damper coefficient IJ, and then we have the length of the strut. So this kind of gives us an idea of how long is the spring, what's the normal length of the spring, and finally the direction from mass I to mass J, which is this normalized vector x, ij. Now there's two forces at work here. The first is the spring, and so this is relates the spring coefficient K times whatever the current length is minus the normal length of the spring, L 0 superscript here, times the vector x, so that's the direction, so we have a directional for this force. And the second thing is the damper, and so this relates the velocity. So unlike the previous one, which is distance, this is now velocity, and the what we can use now is Newton's third law, that forces have equal and opposite reactions. So if we want to find out as we have what the force on mass I is, well, we want to figure out what the force on mass J is. So it comes out that we flip the sign, so the force for mass J for the spring is minus force of the spring for I, and same for the damper, we just take the negative force for mass I. And by simulating the system, we can essentially determine what happens for two masses, what the forces ought to be. Okay, so now let's talk about how we might use this, connect them together into a mesh. So we may want to connect these struts as part of a mesh in order to have a springy deformable mesh. And what we want to do is let's take a look at an example system. We might have 4 vertices or 4 particles, and they're connected with these 5 springs in this figure. And so we need a way of creating a data structure. And so one of the requirements for this data structure is we need to capture the strut parameters. So we need to capture the spring coefficients K, the damping coefficients D, their lengths, and we need to encode this somehow relating all of these particles. So in this case we have 5 struts, so we would expect this data structure to hold 5 bits of information. And second, the faces. So the faces are the 2 triangles formed from this system. Maybe we're simulating a flag or something like that. So in this case we have 2 faces, so our data structure needs to hold information about what the neighboring vertices are, what the neighboring struts are, and so on. And then we have the vertices, which in this case we have 4, so 0, 1, 2, 3, and 4, and that stores probably the neighboring struts that contribute to, or it can contain the neighboring struts that contribute to that vertices, so we can add the forces together because we're simulating the particles here. So there's an element that we think about is structural rigidity, and what I mean by this is that if we have a box that has springs, there's nothing that's keeping this box together, and so what could end up happening is it could end up just kind of going over flat because there's nothing holding it up. So a lot of times we might have to add extra struts where we kind of add extra springs holding the box together to kind of add some rigidness to it. There are other methods, such as using a better primitive, like a tetrahedron, all right? And the whole idea here, essentially, is then we also have to calculate, we haven't talked about mass, but we would also want the mass to distribute through the object as well. And so in order to do that, we would say perhaps we have n vertices and we have a total mass of m, so we said that each particle has m over n. That's the total mass for each particle. And then that helps us determine what those spring coefficients ought to be and damping coefficients, because we would initially want the structure to kind of maintain its shape. So this becomes a little bit trickier when your models start to get more complicated. So another way than just simulating a bunch of struts between particles, which works for smaller cases, is to do torsional springs. And so torsional springs are a way for us to get around the problem that struts are going to have scalability issues when we get too many of them. So the way that torsional springs work is through the use of torque, essentially. And so we will want to go ahead and instead of simulating just merely the springs, we could simulate hinges, essentially. So we have polygons on hinges, and we have their normals, and we have this h vector, which is the hinge vector that the spring, that the faces can twist about, that represents that central axis. And then we can go ahead and figure out what is the ideal angle between the two. So we can relate the normals n1 and n2 with a default theta angle between the two faces. So this is a sideways view. And then we can go ahead and calculate, well, what is theta? And so it turns out if we take the inverse tangent of the cross product between n1 and n2 divided by the dot product of n1 and n2, and then take the dot product with the h vector, which is the hinge vector, then we can figure out what is the initial angle, what should that be. And so that helps us find these perimeters a little bit easier. And then we can calculate the torque, which is then the torsional spring constant k theta times theta minus theta naught times h, where theta naught represents that initial angle that the polygon should be at. And so this is pretty flexible and easier to implement when you have too many struts. Okay, so we're going to talk about two applications here. One is some lattice deformers, and the second is cloth. So lattice deformers are a way of handling the problem that our geometry is very complicated, and we don't want to have to set up parameters for this entire system. So one thing we can do is we could take our large mesh, and instead of simulating deformable mesh with that particular model, we could actually create a simpler version with a lattice system. And so Cedarberry and Perry in 1986 came up with this idea of freeform deformations, FFDs. And the idea is that we might have a complicated model, and if we stick it inside of a lattice, then we could associate the lattice with each vertex of the weight that it ought to have. And then we can easily, by manipulating the lattice, then deform the model inside the lattice. And so what this allows us to do essentially is simulate a smaller model rather than the entire mesh and apply it. So if you wanted to have like a springy looking or a bouncy looking 3D animated character, then you might want to use a lattice deformer to accommodate that. Or if you want to simulate the stretch and squash animation effect, then you can also apply this model as well. And it's very effective. Probably a lot easier than to try to do struts for a large complicated mesh, especially since a large complicated mesh, the smaller that the edges get, the higher the spring constants have to go, and essentially you can create a lot of oscillation in the system or make it very hard to kind of manipulate. So lattice deformers are good for manipulating objects that have volume, but what if we want to do cloth, which is more of a two-dimensional thing? So let's just talk about that idea real quick. So cloth is kind of unique because it's more of a flat type of surface, and some earlier research Breen et al. In 1992 wrote this paper, A Physically Based Particle Model of Woven Cloth. This is kind of influenced a lot of later work in terms of using particles to simulate cloth. And then there's another one. One of the problems, though, is that even though the particle system was doing pretty good, it was still kind of difficult to simulate cloth for animated characters. So, in other words, we couldn't get time steps large enough. So Bariff and Woodkin in 1998 wrote this paper, Large Steps in Cloth Simulation, kind of helped solve this particular problem. Now, there's been lots of cloth research in recent years, and we won't go into the research details there, but just to kind of talk a little bit about this. The first one, of course, we're talking particles, and the second one, time steps. So these are two of the big issues that you might want to solve as you're going into cloth. But with cloth, you have this weave. All right, so if we were to like zoom into like a regular plain weave of a cloth, we essentially have two kinds of fabric. The one is called weft. This is what gets woven inside. The straighter ones called the warp. And essentially, when the loom comes undone, then the tension, the warp pulls all the yarns together, and so everything's kind of held together by friction. But this is kind of the reason why cloth is kind of hard to simulate, because it's really a mechanical structure and not just a simple, it's not something that you can just apply maybe a bones or some other type of thing to kind of simulate. So the way that we might want to do this using the particle system is essentially just replace this by a grid of particles and then simulate the interaction between the two. Okay, so there's three particular types of forces that we have to keep in mind for cloth. The first is tensile stretching, and what this is essentially is when the cloth is being pulled in one direction. And then secondly, we have out-of-plane bending, where essentially, if you just imagine the cloth being folded over your hand or over a clothesline, this is out-of-plane bending. In other words, if you had one plane for the cloth and you bent it, then you'd have two planes. And the last one is in-plane shearing, and this has to do when you kind of pull one of the particles, almost if you lay the cloth flat on a flat surface and pull on the middle, you'll notice that this is kind of in the plane and is moving a little bit. So with cloth, essentially, we have different forces to kind of keep in mind before we're able to kind of work with them. Now, the reason why the struts won't work exactly as intended with this particular model is because of the tensile strength. So if you were to take a handkerchief or some cloth and you pull it one direction, you'll find that it's extremely difficult to pull it in the other direction as well. And that's because, unlike the spring model, the strut model, we would expect stretch in every direction, all right, not just one. So with this in mind, if you're going to work with cloth, you have to make sure that you spend some time picking values that work for the for cloth. So you want to try to use measured forces, okay? And in particular, over here, if we looked, we have an R, so that represents that length there, and then we might have an angle, and lastly, we might have these distances, phi, and these are some of the forces that are used, or rather parameters that are used in the forces. So let's go ahead and review. Okay, so we talked about struts, which is kind of an extension of the mass spring damper idea, and we are able to kind of connect these in meshes by using particles, but we can use we can represent faces, and we can represent vertices and so on with this particular idea. And we noticed that you might have to add extra struts to kind of help keep the stability for smaller objects, but as you want to get more complicated, you need something more useful for the job. So we talked about torsional springs, which essentially use a hinge around the faces and use that to control the stability. And then we talked about two other applications for lattice deformers. So perhaps we can just use a simplified model rather than use the original mesh, and then that allows us to kind of do squash and stretch and so on using a lattice. And then lastly, we talked about kind of what goes into cloth simulation, namely that we can use a particle representation, but we have to think in terms of tensile stretch, out-of-plane bending, and in-plane shearing because of the woven structure. So a lot of different areas to kind of work with over here, and hopefully this has been interesting to you. So I'd like to go ahead and say thank you and adios.